Hi everyone, I'm Chris and welcome back to the lecture on support vector machines of this machine learning course. This section is all about soft margin. So far, we considered the idea of the support vector machine and the mathematical formulation behind it. The support vector machine was used for separating two classes, class A with y equals -1 and class B with y equals +1. We introduced a pseudo-model function y tilde equals the parameter vector w transposed times the vector of the input variables x plus the parameter b. For y tilde equals 0, this is a boundary equation, though this is the model of the support vector machine. Further, for y tilde equals +1, we have the plus margin boundary, which limits the margin to class B. For y tilde equals -1, we have the minus margin boundary, which limits the margin with respect to class A. The margin is the space without any data points around the separating boundary. We use the support vector machine to classify two classes with a separating boundary. This boundary has a linear shape by its construction. But what if there are only a few data points which violate the linear separability of the classification problem? This situation is sketched on the lower left. Only a single light blue data point is among the dark blue dots. Without it, we could apply directly the support vector machine. However, so far, our margin does not allow data points to be within the margin or on the wrong side of the separating boundary. This is called hard margin. We could use a variable transformation, but this seems not appropriate if only a few outliers violate the condition of linear separability. More appropriate is to weaken the hard margin constraints and allow a few data points to violate our strict separation conditions. This leads to the so-called soft margin. Thereby, we have to find a trade-off between misclassified data and a maximal margin width. This procedure allows to apply the support vector machine to problems even if a few data points violate our constraints. To quantify the misclassification, the so-called slack variables are introduced. Now, let's consider a simple one-dimensional example where a single light blue data point is among the dark blue data points. Our pseudo-model function y tilde has a certain value at the location of this data point. This value measures the misclassification with respect to the separating boundary. It is 0 at the boundary and increases linearly outwards. However, our constraints state that the data points should not only be on the correct side of the separating boundary, the data is even not allowed to be within the margin. The pseudo-model function is -1 at the minus margin boundary. Therefore, we shift this function upwards by 1. The corresponding value defines our slack variable value xi for this data point. So the value is 1 plus y tilde. This expression measures the misclassification with respect to the minus margin boundary. The contribution xi decreases if the data point is closer to the minus margin boundary. At the minus margin boundary, the value is 0. On the left side of the minus margin boundary, the measure of misclassification should be 0, so we set xi is equal to 0 for all points on the left side of the boundary. In total, we have xi I equals 0 on the correct side of the margin boundary and xi I equals 1 plus y tilde otherwise. So far, we considered only misclassifications of the light blue data points of class A. To incorporate class B as well, we write instead of 1 plus y tilde, 1 minus yi times y tilde. yi equals minus 1 for class A. These are the light blue data points. So this holds our previous considerations, and we still have 1 plus y tilde for class A. However, this more general expression also holds for class B. We can substitute the pseudo-model function y tilde equals the parameter vector w transposed times the vector of the input variables x plus the parameter b. The cost function is modified to include the slack variable into the model. The first term, 1/2 times the parameter vector w squared, still wants to maximize the margin width. The second contribution, c times the sum over all data points of the slack variable values, incorporates the amount of margin violation. So minimizing the cost function needs to balance the maximization of the margin and at the same time not too much violation of the separation of the classes. The new hyperparameter c specifies this trade-off. Large values for the hyperparameter c lead to a hard margin. This is because of the large contributions of the slack variables measuring the misclassification. Small non-vanishing values for c lead to a soft margin, which allows for more violation of the margin. Now let's check our constraints. yi times the parameter vector w transposed times the data vector xi plus b is greater than or equal to 1. These constraints are modified to allow for violation. The slack variable for the corresponding data point is subtracted on the right side. When we take a look on our definition of the slack variable, we can see that the data point on the correct side still gives our original constraints. So for xi I equals 0, we have our original constraints. However, for a data point on the wrong side, we can substitute xi I into the constraint inequality. The 1 cancels out, and on both sides we have yi times the parameter vector w transposed times the data vector xi plus b. Consequently, even the misclassified data points hold the constraints. So we don't really need the constraints if we use the definition of the slack variables. There is a more concise form to express this definition of the slack variables. Xi I equals to the max value of 0 and 1 minus yi times the parameter vector w transpose times the data vector xi plus b. The functional relation is displayed in blue in the sketch on the upper left. It is called the Hinge loss. We can substitute this into the cost function. So this is the final cost function for soft margin support vector machines. Note that we can derive also a dual formulation for this soft margin cost function. Section finished. Thank you very much for listening. If you like this video, please click the like button and consider to subscribe this channel. If you have any questions or comments, please leave a comment down below. So thanks again and see you in the next section.